Assalamualaikum warahmatullahi wabarakatuh. My name is Zarif Ilman bin Najafri. I'm a final year student in Bachelor of Science, Honors Physics, and the title of my final year project is Morphological and Electrical Properties of Zinc Oxide Nanostructures Growth on Glass Substrate. I am supervised by my lecturer, Dr. Zaina binti Muhammad, and this is my online presentation for my final year project. So this is my content for my online video presentation, which consists of introduction, problem statement, objective, methodology, result and discussion, and last but not least is conclusion. First, let's begin with introduction. Zinc oxide is a semiconductor material with a direct bandgap semiconductor 3.27 eV and large exciton binding energy of 60 MeV at room temperature. Nanostructures are known as material or structures that have at least one dimension between 1 and 100 nanometers. Zinc oxide nanostructures are among the most important functional oxide nanostructures due to their excellent physical and chemical properties, such as high mechanical and thermal stabilities and electron confinement properties. Next is problem statement. Good crystallinity is necessary information of zinc oxide nanostructure because it can allow for a faster and more direct charge transport pathway which improves charge carrier transport. With respect to nanocrystal size, shape, crystallinity, and nanostructure orientation, the electrical conductivity of zinc oxide nanostructure steadily increases. The next one is objective. The objective of this study is to investigate the structural and electrical properties of zinc oxide nanostructure growth on glass substrate using different concentration of zinc nitrate. Then we continue with literature review. Tan et al. Using the simplified hydrothermal process in which the conventional autoclave system was replaced by a low-cost setup using sealed glass vials stated that the average diameter of nanorod was found increased from 45 to 78 nanometer when the concentration increased from 0.01 to 0.05 molar. Next, Abdurrahman et al. Conducted a study using modified chemical batch deposition method. By varying zinc oxide precursor concentration, the average length of grown zinc oxide nanorods increased and the diffraction peaks along the 002 plane got higher, sharper, and narrower. The next one is Philip et al. That synthesized zinc oxide nanostructure by using the microwave-assisted hydrothermal method on ITO-coated glass substrate expressed that the IV curve of the compact arrays zinc oxide nanostructures exhibited excellent ohmic contact and better conductivity in the case of sample grown over RTA-treated seed layer because of the larger surface area and therefore greater surface carrier concentration. Next is the methodology of the study. The method that used in the study is hydrothermal method. And this is the flowchart of the hydrothermal method. Then we move to result and discussion. Firstly, X-ray diffraction XRD. The zinc oxide nanostructure generated have a preferred crystallographic 101 orientation. The peak of the XRD pattern shows a minor shift to the left when the concentration increase. The zinc oxide meshed well with the wozet zinc oxide and all of the diffraction peaks could be indexed as hexagonal wozites. The peak intensity of sample zinc oxide prepared by using hydrothermal method increased when the molarity of the concentration is increased, but the peak intensity at 0.12 molar, 0.14 molar, and 0.16 molar showed that there was no significant difference. Sample for 0.14 molar is the highest peak intensity, indicating that there are more crystal structure and better morphology of the oxide compared to other samples. The peak intensity can be calculated by using formula peak intensity equal to intensity divided by sum of the intensity. The crystallite size can be calculated by using the Debye-Scarer equation, which is D equal to 0.94 times wavelength divided by FWHM cos theta. This is the table to theta of 101 peak, f'(m), crystallite size, peak intensity for 101, and lattice constant A and C. The crystallite size decreases when the molarity of the concentration increases until 0.12 m, then the crystallite size begins to increase. Hence, 0.12 m sample is the smallest crystallite size, which is 24.14 nanometers compared to other samples. The second one is Fourier transform infrared (FTIR). Peak with modest intensity observed at 1370 can be attributed to the functional group CO of asymmetric and symmetric stretching vibration. This peak might also indicate the presence of impurities and moisture. The peaks around 899 are associated with the symmetrical stretching modes of ZnO Si bonds, and it increases when the molarity of the concentration increases. The peak in 1740 can also be linked to another common band associated with the bending mode of absorbed water. Next is UV-VIS spectroscopy. The transmitters in visible and ultraviolet wavelength regions are obtained in the wavelength range of 300 to 800 nanometers. Sample 0.12 m show the highest transmitters compared to other samples. Meanwhile, the lowest transmitters belong to sample 0.10 m. Reduction of transmission spectra is due to particle size increases, hence reduce the grain boundary area. Last but not least is IV measurement. The current intensity of 0.12 m nanostructure show good current intensity and low resistance compared to other samples. As a result of the greater surface area, 0.12 samples also exhibit high conductivity. Higher conductivity results from increased surface area and surface carrier concentration. Sample 0.16 is the highest resistivity compared to other samples because of the larger crystallite size, smaller surface area, and hence fewer oxygen vacancies. In conclusion, the morphology and the structural properties of zinc oxide nanostructure growth on glass substrate was successfully studied by hydrothermal method. Based on the SRD result, sample for 0.14 is the highest peak intensity, indicating that there are more crystal structure and better morphology of zinc oxide compared to other samples. 0.12 samples is the smallest crystallite size, which is 24.14 nanometer compared to other samples. For UV-VIS spectroscopy, sample 0.12 show the highest transmitters compared to other samples. Meanwhile, the lowest transmitters belong to sample 0.10 m. From the IV measurement, 0.12 m nanostructure show good current intensity, low resistance, and exhibit high conductivity because of greater surface area. So, that's all my presentation video. Thank you.